I am Burak Topçu. Today I will present the GPU runtime memory performance and power monitoring tool, which is GPPRMon. I'm from the computer engineering department at Izmir Institute of Technology. As you know, the data processing task, especially today's data processing tasks, require high performance and energy efficient heterogeneous computer system, and the GPUs play a crucial role to accelerate these systems as an accelerator or coprocessor. And literature addresses the overall energy consumption and runtime power issues for the GPU-based systems more, day by day. Here on the table and the figure, you see the GPU system share as a GPU system usage in the accelerating system. GPUs are utilized as accelerator or coprocessor or in those systems. As you see, the NVIDIA products dominates the GPU usage. I took these statistics from the top 500 HPC. However, there are still some catastrophic performance and energy efficiency problems, especially for the execution of memory-intensive workloads. First of all, the memory wall problem still exists, and the proposed solutions for performance and energy improving solutions compete with each other. And to become beneficial design decisions, there should be more analytical observations. Secondly, the recent developments such as tensor cores, concurrent kernel executions on clouds, or shader execution reordering implementations makes GPUs complicated, and to identify performance bottlenecks of those GPUs, complicated GPUs, more detailed research needs to be done. Here is my outline. I will begin with an executive summary. In the executive summary, I will mention the literature problems. I will mention our motivations and contributions. Then I will continue with the background section. In the background section, I will provide some brief information related to GPU programming environment, GPU architectures, and state-of-the-art GPU simulator. Then I will introduce the GPPRMon, the methodological overview of methodological background of the GPPRMon, collected microarchitectural and performance metrics, which is collected by GPPRMon. Then I will continue with the metric collection and visualization configurations of the GPPRMon. GPPRMon includes general view, temporal view, and spatial view options. Then I will give you a descriptive case study which exemplifies how to use the GPPRMon and how to extract the performance bottlenecks empirically. Then I will conclude my presentation. And as you all know, none of the NVIDIA GPU profilers such as Nsight Compute Tool or Airside Systems, or the simulators such as GM5 or the GPU Sim directly reports the runtime GPU performance and power consumption, and evaluating GPU application performance based on the kernel performance metrics hides most of the detailed observations. And contemporary approaches to investigate GPU execution behavior at lower executable granularity, such as thread block level or warp level or the instruction level, are not insufficient today. Additionally, in literature, researchers implement several in-house target-specific repetitive works by extending the simulators to monitor the runtime performance and power consumption, and these causes a redundant effort in literature. Here our motivation is to provide a tool monitoring GPU execution temporally, runtime snapshots of the GPU execution, and spatially, because the GPU is a complex and big device compared to the multi-core architectures, and track the power dissipation at runtime. One of the main motivation is to support all official NVIDIA GPUs supported by the simulator. In this way, we aim to highlight the performance bottlenecks empirically with various execution granularity. We will provide monitoring options at thread block level, warp level, instruction level, thread level, etc., at kernel level, etc. And we hope to save the researchers from the repetitive in-house efforts, which is applied to identify the performance bottleneck for their research. Our contributions with GPU is that our contribution with the GPPRMon is that GPPRMon, which is built upon the GPU sim, is a runtime, performance, and power monitoring tool for GPU executions. GPPRMon provides multiple configuration options depending on the researcher's expectations. GPPRMon visualizes the GPU execution with various views. I mean, it provides various viewing options. Lastly, GPPRMon is beneficial to identify the overall and temporal performance bottlenecks of GPU executions by pointing out the activation of the smallest execution elements, I mean the warps, for example. We also provide a case study describing how to use and utilize GPPRMon. Here is the NVIDIA GPU programming environment. On top of that, you see a CUDA code. Here is the CUDA code. CUDA allocates some memory locations pointed by these pointers and size of them. Allocates the memory from the GPU memory. Then it assigns some thread per block and thread grid dimensions and launches a kernel. Here is the vector is a kernel call. Inside the kernel, it acts depending on the thread specific variable, thread identifier. For example, this is a thread identifier. This adds the each array element represented by the each array element pointed by the thread block thread ID and summed up and writes the result to the C. This is the compilation option of this kernel. After compiling and building the executable, you may extract the PTX and SAS executables. SAS is the real machine code. However, we don't have detailed descriptions. I mean the operational code, registers, etc. We don't have these documentations which are not provided by the NVIDIA. We utilize the virtual machine instructions, which is the PTX, parallel thread executables. For example, these are the PTX instructions. Those instructions loads parameter from the parameter memory unsigned 64 bits to those registers. Then these are the move operators, etc. It goes like something like that. When you launch a kernel, it creates a kernel consists of the same instructions, consists of thousands of threads which execute the same operations instructions. This is the 3D grid visualization. Inside each grid there are multiple thread blocks, and inside each thread block, for example this is a thread block, inside each thread block there are threads. Here the thread block may also configured as 3D. Inside each thread block there are threads, and each will operate privately. This is an typical NVIDIA GPU architecture. Inside the NVIDIA GPU device, there are streaming multiprocessors, and L1 data cache is located on those streaming multiprocessors. There are L2 cache and global memory. These are the main memory components. However, there are also constant and texture memory units. Inside the streaming multiprocessor, there is an instruction cache, there is an L1 cache, there are multiple warp schedulers and instruction dispatcher units which dispatch the instructions to the functional units. Most of the functional units are the ALUs, basic ALUs, which conduct single precision or double precision operations. However, there are some specialized functional units which calculates the specific mathematical operations such as logarithmic or exponential functions. There are also some load store units which conduct the memory operations inside those streaming multiprocessor units. This is the simulator for workflow of the GPU architectures. This is the GPGPU sim implementation, by the way. In the GPGPU sim, the instructions are fetched from the instruction cache and decoded. After the decoding stage, it puts the instructions within the instruction buffers. These are the valid bits, these are the ready bits, and these are the instruction specific informations. Whenever the issue unit issues an instructions via the warp scheduler, it fetches the instructions from the instruction buffer, the decoded instructions from the instruction buffer, then transmits them to the related functional units. For example, the related functional unit may be ALU or load store unit or the tensor core. These the related functional unit is dependent according to the operational costs of those verbs. Inside the load store unit, if the memory operation conducts, if the instruction will conduct some memory operation, first of all its address is generated, then it transmits to the coalizer unit in order to merge multiple memory access to the one. Then if the L1 data cache is bypassed, it transmits them to the interconnection network to access L2 or DRAM. However, it will firstly visit the L1 data cache, otherwise then the memory request will continues to the lower levels of memory hierarchy via interconnection network. This is the GPPRMon methodology. The GPPRMon is built upon the cycle accurate performance model of the GPU sim, which is the Axel sim, and the power model, which is the Axel watch of the simulator. You need to specify a configuration file before the simulation. It specifies the simulation and metric collection options. Whenever a kernel launch, the memory profiler, the performance profiler creates a class to collect separate metrics. Within each sampling frequency, it exports the collected metrics. You need to specify the sampling frequency inside the configuration file. These are the exemplifier visualization of the collected metrics. For example, the instruction monitor shows the instruction specs, instruction issue and completion cycles, thread block IDs, cluster IDs, and warp ID. Similarly, these are the collected metrics within each sampling frequency. Similarly, these are the collected power measurements within each sampling frequency. In parallel with the metric collection, the visualization executes by utilizing the collected metrics. In the visualization stage, there are three visualization options. One of them displays the general view of the execution, GPU execution, and the other one shows the spatial and temporal views visualization. This is the configuration options. These are the tables showing the configuration options for metric collection and visualizations. On the left side, you see the configuration options for the performance microarchitectural performance metrics, and on the below side, on the bottom, you see the power spatial metric collection configuration options. On the right side, these are the visualization configuration options. Whenever you enable the memory profiler and power simulation mode, the simulator starts to collecting microarchitectural metrics and performance power dissipation metrics. You need to specify a sampling frequency for both performance model metric collection and runtime power model metric collection. Additionally, you can collect IPC, cache metrics, DRAM row buffer utilization, and instruction monitoring metrics by enabling these options in the configuration file. You can also activate the store enable flag, which adds the metric collection of the store operations among the memory operations. You may also accumulate the statistics or aggregate the statistics for both performance and power models. However, if you aggregate the statistics, the runtime behavior may disappear because it converts to the average kernel performance. You may also activate the dynamic voltage frequency scaling for the power model. For the visualization options, plot GPU will generates the general overview of the visualization stage. Plot memory hierarchy will display some spatial utilization of the memory hierarchy, and plot core will display the temporal issue completion statistics of each thread block. And the sampling frequency is a bit different from what we did in the simulator stage. This sampling frequency determines the visualization samplings. You need to specify a GPU name for the visualization option. You need to specify the simulation output of the performance model, and you may specify some thread block IDs, which is displayed by plot core configuration. You may also display all the thread block statistics as well. this is the general view visualization. In the general view visualization, you see the memory access statistics for L1 data cache, L2 cache, and DRAM, kernel specs such as the kernel ID, cycle interval of the snapshot, grid and block dimensions of the kernel, and the number of the active SMs in the corresponding GPU. The performance metrics, these are the performance metrics, and the IPC is another performance metric as well. And the dissipated power, as I said before, we mostly focused on the runtime dynamic power consumption here. You see that the power is collected for each component separately, and this is the overall power consumption throughout this cycle interval. The temporal view displays the thread blocks execution, SM performance, and power dissipation of the streaming multiprocessor components. As you can see that these are the instructions for a thread block. For example, the instructions here pointed by the 368 is a load global variable from the global memory DRAM. The data which is loaded from memory is 32 bits. This is the operand, and these are the issue and completion times. The first row shows the issue time and second row shows the completion time. These ones are the warp ID within this thread block. For example, this is second thread block. These are the first warp, and these are the second warps as well. This thread block executes on the second SM streaming multiprocessor. The IPC rate within this SM is the 3.7 here, and this is the L1 data cache statistics of this SM. This is not an average L1 data cache statistic. This just represents the L1 data cache access statistic for this second SM. This is the cycle interval that shows the issue and completions. For example, this cycle interval shows the execution of 500 cycle, and inside this 500 cycle, these instructions are issued and completed. This is the spatial view of the GPPRMon. Spatial view shows the memory access utilization of each memory component separately. For example, this is a GV100 memory hierarchy visualization. Inside this hierarchy, there are 80 L1 data cache, there are 32 memory partitions, and inside these memory partitions there are two L2 data cache, L2 caches, and DRAM banks. As you can, these colors represent some utilization statistics. For example, blue represents the intensity of the reservation failure, which means that the misses cannot be allocated due to the resource insufficiency. However, L2 caches here utilized in a good way because the hit rates are comparably bigger. However, the other L1, L2 caches cannot utilize similarly. By utilizing this figure, you can see the utilization statistics of each memory unit separately. For example, some of the L2 caches utilized in a good way. However, some of the L2 caches are not utilized in a good way. On the middle side, the row buffer access statistics of each DRAM bank is shown. Whenever the color turns to white, states that hit rates gets bigger. However, whenever it turns to purple, it states that the miss rates increase. Here is a case study to analyze the performance bottlenecks by utilizing the GPPRMon. In this case study, we utilized the GV100 GPU, and we utilized the page ranking algorithm experimented with the Web Stanford data. Inside the GV100 GPU, there are 80 SMs. These are the specs of these SMs, and there are 32 memory partitions. Inside each SM, there is 128 kilobyte L1 data cache and instruction cache, and inside each memory partition, there are two L2 caches and one of the L2 cache is 96 kilobytes, and there are 1 gigabyte DRAM banks inside each memory partitions as well. The page ranking algorithm assigns weights to the graph nodes depending on the relative importance among the nodes. It processes here the Web Stanford data, which is a memory intensive workload. As you can see, the overall performance statistics, the contribution kernel and linear normalization kernel have high IPC, dramatically high IPC compared to the pull step, which is the first kernel. We need to resolve runtime performance bottlenecks of the first kernel. As you can see, the IPC is 3. The miss rate is L1 data cache miss rate is high. However, the overall L2 cache miss rate is comparably low. And the most of the cycles elapsed throughout the execution of these 3 kernels. The most of the cycles is consumed by the first kernel, as you can see. I merged multiple temporal view of the thread blocks inside the zeroth SM. These are the 24th, 104th, etc. All of these thread blocks executes on the zeroth SM concurrently, and I selected 2 instructions, 2 load operations inside each these thread blocks. The first row shows the issue completion times of the first instruction, and the second row shows the issue completion times of the second instructions. As you may realize, the first instruction tries to load 64 bits from the memory. However, the second instruction tries to load 32 bits. The first instruction tries to load a bigger variable. Hence, it's probably to create bottleneck on the memory hierarchy by this instruction is more. The ideal L1 data cache access cycle is 20-25. Ideal L2 cache access cycle is 180-190, and ideal DRAM access cycle is 280 and 290 cycles. However, as you can see, for the first instructions, these load operations causes long latency memory operations for each thread block. For example, I've selected an operation's issue completion times. There is the difference between issue and completion times is bigger than 100-500 cycles, which is the long latency operations. By utilizing this temporal view option, you can see the issue completion times of each warp memory operation. The first observation here is that the efficiency of off-chip memory workload handling, off-chip memory traffic, has a crucial impact on overall performance, because the L1 data caches are private within each SM. However, the off-chip memory partitions are being handled by all the SMs, and which harms whose performance harms due to the traffic of those SMs. Also, I displayed the runtime memory access statistics within from 0 to 100 cycles. As you can see, the hit rates at the beginning, the statistics oscillates. For example, the reservation failure oscillates till here, and there are some reservation failure problem here. Then reservation failure gets decreased. Whenever the reservation failure gets decreased, the hit rates and miss rates will reach an equilibrium and continues in this way. For the L2, the hit rates reach a stable point. Then all the L2 cache access result in hits. Row buffer access statistics oscillates throughout the execution. This is the spatial view showing the memory utilization of some of the L1 data cache, L2 cache, and DRAM row buffer units. All the units are the same for the different snapshots. There are 9 snapshots showing different execution intervals. As you can see, at the beginning, data cache causes misses. Then those misses turns to reservation failure at the second snapshot. at the third snapshot, the reservation failures solved and L1 data cache casus hits. However, the L2 cache gets worse throughout the execution. Here, the critical point is that the runtime behavior changes throughout the execution, and the spatial views shows the utilization of each memory component separately. I mean, for example, in the 7th snapshot, while one of the L1 data cache causes high misses and the other L1 data cache does not cause that much miss in this 7th snapshot. The second critical key observation here that the memory utilization behavior changes temporally, as I showed first, second, and third snapshot, and spatially, as I mentioned in the 7th snapshot as well. These are the runtime power consumption statistics of the SMs and memory partitions. Memory partitions include those are the DRAM elements, L2 cache. These are the sub-elements of the DRAM, and interconnection network. These are the streaming multiprocessor components. As you can see, when the execution continues, the streaming multiprocessor overall power dissipation of the streaming multiprocessor gets decreased, because most of the time these streaming multiprocessor waits for the data from the off-chip memory hierarchy, and the off-chip memory hierarchy power consumption gets increased when the execution goes on. To conclude, in this work we propose a runtime performance and power dissipation monitoring tool, which is the GPPRMon. GPPRMon helps us to collect several microarchitectural metrics and provides us a multifunctional visualization options, which allows us analyzing the execution from various perspectives. We also provide a performance bottleneck analysis of a sparse graph workload, which is the page ranking algorithm on GVUs, on GV100. We describe here how to utilize the GPPRMon. Hopefully, this work helps us to overcome additional in-house works to conduct analyze for baseline and solution performance analysis of among the baseline and solution implemented versions. And for the future, expansion of this work may be done by integrating the CUPTI, which is the performance metric collection library of the NVIDIA, and the collected metric may be integrated with the GPPRMon visualization options as well. Thank you.